Welcome back. In the previous video, we showed that given some constructible number, we could divide it by any integer. We're now going to use this to show that in general, we can divide any constructible number by any other constructible number and essentially construct that quotient. So in order to do this, we're going to use a certain special process. But first, so let's suppose that, it was the numbers a and b. We want to figure out what a divided by b is. Okay, well, in order to do this, we're going to actually want to work with numbers that are smaller than our unit distance. So we know that we can do this by the earlier construction. We know we can find some number n such that a divided by n and b divided by n are smaller than positive 1, our arbitrarily chosen unit. So we're going to take these numbers to be x and y. Now, what we're really going to determine is this quotient x divided by y. But of course, I mean, this is just a divided by n over b divided by n. And so this will actually give us the ratio that we're looking for after all. Okay, so in order to construct this quantity, we proceed by first drawing some arbitrary straight line. So I'm going to mark a point here, I'll mark a point here and here. Now, again, we're supposing that y is a constructible number. So we could have, the idea is to choose this point, which we know that we can simply copy distances to have been this previously constructed y. We're also then going to erect the perpendicular bisector through this point y. So I actually showed you how to do this in the previous video, so I am going to cheat in this instance just for the sake of time. Don't want to bore anyone to death here. But we're gonna, so of course you extend the line further than you think you have to, and then you just copy the distance x, which we can do because we're assuming x to be constructible along this line. And this final point is chosen so that it is the unit point, which of course we know is constructible, and we know is going to be to the right of where y is because of our assumption that we've rearranged, constructed these numbers so that they are less than 1. And then again, skipping over the process of constructing the perpendicular bisector, one then creates the perpendicular through this point at 1. And finally, simply draw the line between these 2 points up here. And now the claim is that this distance here is the ratio that we're looking for, x over y, which is a over b. So in order to demonstrate the claim, I mean, we just need to do a little calculation. Well, notice this smaller triangle here is similar to this larger triangle that we've created. So we know that the ratio of x over y is equal to the ratio of, for now, we'll just call this the mystery side, z over 1. Well, of course, z divided by 1 is just 1. And so we see that, in fact, the length of this mystery side is actually the ratio that we're looking for. So great. We were able to take the fact that we can divide any constructible number by any natural number and extend this to the result that's saying that given any 2 constructible numbers, we can construct their quotient. And so you might be thinking, well, if we can construct division, can we construct multiplication? Well, certainly. And so in order to do that process, to construct an arbitrary, a product of arbitrary constructible numbers, we begin again. We're just going to make some arbitrary line and some arbitrary other line coming off of it. And again, make your lines longer than you think you should. I should probably extend this line just in case. And the process for this is you begin by creating your unit distance. So this first segment of the line, I know my hand, it's in the way sometimes, but it won't be in a moment. This first segment of the line will have distance 1. Then the next point will be constructed so that it has distance x. And then finally, you want to construct a point which has a distance y. And of course, all of these are possible to do because we're assuming x and y are constructible numbers. And of course, we can construct our arbitrarily chosen unit. I mean, that is simply a definition that we create. Okay, so in order to go through this process, now, again, I'll be skipping over all the perpendicular bisectors. Please just see the first video. We construct the bisector passing through the point at distance 1, the point at distance x, and the point at distance y. Now, in the previous video, we also saw that there's an angle copying construction. So we're going to use that here. First, you're going to take this first intersection point of the new 3 that we've created, and you're going to draw the line that comes up here from 1 over to the point at distance s at the bottom. Just like so. And now we apply the angle copying formula that we used from the previous section to this angle right here, and you're going to copy it over here at the perpendicular line, which intersects right at the point of distance y. So again, just for the sake of time, I am going to cheat, review the first video to see how to actually do the perpendicular bisection. And then my claim is that the distance from this corner to this final point that we've created, this is going to be a point at distance x times y. So perhaps we'll call the full thing z here. Okay, so in order to see that this is the case, again, we're just going to go through some algebra, and geometry and algebra, and it comes down to similar triangles as well. So it all has to do with this angle. And if I'm going to make this first perpendicular h, this next one will be capital H, and this one will be math bold h. And so notice that all 3 of these triangles, this one, this larger one, and this largest one, are all similar. So writing out the similarity relation, we know that 1, the length along the bottom here, divided by little h, well, this has to have the same ratio as x divided by capital H, and that must also have the same ratio as y divided by math bold h. And we're actually going to make use of a second similar triangle in the situation, recalling that these 2 lines are parallel, and therefore these angles are the same. And so making use of that similarity relation, we know that the distance along here, which must be, it's the distance x minus this beginning distance 1, so that is x minus 1, divided by the height, which is our little h. This is going to be equal to, well, what's the distance of this triangle right over here? Well, this is our full distance z minus the first part of this, which is distance y. So this becomes z minus y over, and then the height of this is math bold h. So now we can rearrange this formula here by multiplying through by math bold h and dividing through by x minus 1. And this is permissible, right? Because we're trying to construct x times y. Well, we're ignoring the case when x is equal to 1 because that's just constructing y, and we're already assuming that y is constructible. So this gives us that math bold h is equal to h times z minus y all over x minus 1. Okay, great. And then finally, what this means is if we plug this expression in up here, we get that 1 over little h, and then plugging in for y over math bold, this is y divided by little h times z minus y over x minus 1, all in parentheses here. Well, of course, the fraction flips around. So this is just y multiplied by x minus 1 divided by little h times z minus y. And then that tells us, I mean, we can multiply both sides through by little h and z minus y. So we get that z minus y must be equal to, now multiplying this y in here, we get x times y minus y. And then, of course, the y's on either side cancel. And sure enough, we obtain a result that z is equal to the product of x and y. So we've now shown that arbitrary constructible numbers, given an arbitrary pair of constructible numbers, we can always construct their product. Before we conclude and move on to abstract field theory, I'm going to show you that we can construct square roots. So what I've shown so far, I mean, we can have constructible numbers. We can construct their inverses by simply copying that distance to the left of the origin. We can construct products and quotients. We've essentially shown that the constructible numbers form a field. But we still want to show that we can construct square roots. So this is absolutely essential. So in order to do this, let us draw our line and take the origin. And suppose, of course, I haven't kept my compass fixed since the previous video, but, if you have that same paper, you can do this properly by going back and taking your originally chosen unit. So I'm going to just draw an arbitrary point here, supposing this is my unit, right? This has distance 1. And let's say we want to construct we have some number r, which is constructible. So if r is constructible, that means I can create a point B, which has distance r along this x-axis. And then, of course, I want this, take the same distance. And we know that that means I can construct minus r, which will be over here. So I'm going to have, this will be my point A, whose coordinates will be minus r and 0. And now what I'm going to do here is I'm going to take the perpendicular bisector between the point A and the point U. Now, I skipped a lot of perpendicular bisectors, but I really want to make sure I actually get this in the middle for this one. Perhaps I should label my origin here to help us keep track of everything. So I will actually walk through the perpendicular bisector construction for you here. So those of you who are disappointed earlier, now you get to see it. Those of you who are bored, well, you know how to skip ahead to the next part of the video. So we get our intersecting lines, and now the line through here should directly be the point in between A and U. So I'm going to label this this point C once I've constructed it. So here we have our point C. And then now I'm also going to construct, here's where I'm going to cheat again with the perpendicular bisector. I'm going to construct the perpendicular coming through our origin. Now, of course, if you're doing this, you could have been doing this on the original Cartesian system you created at the beginning of these videos. So you could have been working on that the whole time. And then finally, I'm going to take my compass, set it from this point C that I recently constructed over to the point that is unit distance from the origin. And now I'm going to swing this up. And my claim is that this intersection point I've created right here, my claim is that this has coordinates the square root of r. So in order to see this, I'm going to form this triangle between these 3 points here. So I've got my origin, my point C, and this point that I'm claiming here. Now, the total distance from R, or from this point A to the point O, we know is simply just R. And the distance from O to the point U is 1. So that means then that C, so the total distance from A to U is simply R plus 1. And that means that the distance from A to C, because it is the perpendicular bisector, which should be the same as the distance from C to U, is simply r plus 1 divided by 2. But then that means that this distance here, right, we know the distance from C to U is r plus 1 divided by 2. And the distance from O to U is 1. So the distance from C to O should be r plus 1 divided by 2 minus 1, which is r minus 1 divided by 2. So that's our distance down here, r minus 1 divided by 2. And then this point C is the intersection of the circle centered at C, which has this distance here, the same distance as C to U. So we know that the length of the hypotenuse here is actually just r plus 1 divided by 2. So that means the length in question, which I will call y, according to the Pythagorean theorem, this should be r minus 1 divided by 2 squared plus y squared. And that should work out to the hypotenuse squared, r plus 1 divided by 2 squared. Well, that tells us, of course, that y squared must be equal to, so expanding this out, we get r squared plus 2r plus 1 all divided by 4 minus, now working out what this is r squared minus 2r plus 1. But now we're subtracting all of these terms, right? So y squared is going to be the r squareds are going to cancel out. Here I have minus 2, so this is going to be 4r. And here I have 1 minus 1, so those cancel out. I still have a 4 in the denominator. In other words, y squared is equal to r, or y is equal to the square root of r. And there we have it. So this finishes not only that constructible numbers essentially form a field, but in fact, we can take square roots continuously for constructible numbers. So in the next video, we're going to start looking at some slides, and we're going to start talking about the modern perspective of field theory and the beautiful way in that lets us prove some of these ancient results, or conjectures rather. Again, questions, comments, concerns, please leave them down below, and I'll see you in the next video.